This step we're going to work a problem where we've got an ideal gas mixture in an open system undergoing a process at constant composition. So here we go. We've got a gas turbine, and it says that it's, let's see, it says it's adiabatic. It tells us that it's operating at steady state, and things are coming in at 0.35 megapascals, 720 Kelvin, gives us a volumetric flow rate. And those three properties are indicative of the overall mixture, not the components necessarily. Although if we use Dalton's model, the temperature of the components and the mixture are going to be the same. And then we're given the mole fractions of each of those things. And then the gas mixture is coming out at 0.11 megapascals and 380 Kelvin. And there's no chemical reaction here. We've just got CO2, H2O, and nitrogen. So the mole fraction is not changing. The ratio of those components is not changing. All right, so let's go ahead and what are we interested in finding? We're finding the power output, W dot. And before I make any assumptions, I'm not going to really make any assumptions until I have to. So let's just keep on going. So if this were thermo 1, I would identify this as an open system because I've got mass coming in and mass going out, and I would apply my first law because I'm interested in finding W dot. And I can cancel out a few things. Oh yeah, and this is sign convention. We're back to sign convention, not subscript convention like we were using with the cycles. And I'm going to go ahead and knock out the DEDT term because it's occurring at steady state. Tells me that it's operating adiabatically, so Q dot is equal to 0. And I'm going to go ahead and ignore kinetic and potential energy changes. It tells me I can, so I'm going to go ahead and knock those out as well. And so the only thing that I'm left with are the sum of the m dot h's coming in minus the same thing going out. And if I applied my conservation of mass, I would see that the mass flow rate m.1 and m.2 are equal to one another because that dm/dt would go away. And so I could put this in terms of just m dot instead of m.1 and m.2. And instead of just writing h1 minus 2, I'm going to write it a little bit differently, and I'm going to write it as negative m dot delta h because delta h is just h2 minus h1, so it's just another way of writing it. Yeah, just trying to keep with that same terminology of delta H because I'm going to plug in what delta H is for the mixture. So if I look at my equation sheet, I've got a little delta H equation for the mixture, and it's the sum of the mass fractions of each component times delta H of each component. Now if you look at the tables that are available to you, you'll notice that you don't have tables of H values for CO2, H2O, and nitrogen. Well, you got them for H2O, but you don't have it for CO2 and nitrogen. So what do? Well, you do have tables for H bar for all of those things. So those are in A23. If you were in English units, it would be A23E. So what I'm going to do is instead of putting delta H for the mixture in terms of an H that's in kilojoules per kilogram, I'm going to put it in terms of what I have. I've got values for H bar, so it's just another equation on your equation sheet. That's all. You just have to know where to find it. All right, so with that said, let's go ahead and start chopping away at this thing. So let's tackle the m dot first because he's kind of the easiest. So I see on my problem statement that I've got the volumetric flow rate, and that would be a good place to start. So I know that m dot, I know it's the same at the inlet and the outlet, so I'm going to define it at the inlet since I know the volumetric flow rate at the inlet. So I've got V dot 1 over the specific volume at state 1, and the specific volume at state 1 is the specific volume for the mixture. So I'm going to put, let's see, I've got my specific gas constant, which is R bar over the molar mass of the mixture, times the temperature of the mixture divided by the pressure of the mixture. So I've got pretty much everything I need except that molar mass, which I need to calculate. So if you look at your equation sheet, this is equal to the sum of the mole fractions of each component times the molar mass of each component. And the molar masses for all of those components can be found in table A1. And so it's just a matter of plugging things in. And I've went ahead, a lot of times, you could probably drop all those units right there because it's, it's like the mole fractions. It's kilomoles per kilomole, but it's specifically kilomole of your substance per kilomole of your mixture. So you can see how this is all going to break down to kilograms per mixture per kilogram of mixture. So my molar mass is 27.7119, and if I plug that in to my mass flow rate equation, then I get 5.1849 kilograms of mixture per second. All right, so I've got that guy, and now I need to tackle the rest of those. So it's the sum of the mole fraction times delta H bar for each component. So that numerator should essentially have 3 groups of things, okay, for each component. I've got CO2, H2O, and nitrogen. So that's what I've got. And of course, I got the molar mass of my mixture, which I've already calculated, and that's at the bottom. So I know the mole fractions that's given to me in the problem statement. Now I just need to pull out those H bar values. And once again, those are in table A23. So let's look at the temperatures. It's going to be the H bar at T2 minus the H bar at T1. So let's see, T2 is 380 Kelvin and T1 is 720 Kelvin. So when I calculate delta H bar for CO2, it's going to be, well, I've got the H bar at T2, which is 380. So I've got 12,552 minus H bar at T1, which is 28,121, and it's kilojoules per kilomole of CO2. Then my H bar for H2O. Same thing, I'm just going to a different column. So I've got a column for water vapor, and then for nitrogen, got a column for that as well. It's at the very end. So I've got 2 H bars there. And when I plug everything in, this is what I get. And you can see that the units are going to work out really nicely to kilojoules per second or kilowatt. So I've got about 2 megawatts of power that's produced by this guy. And I know that it's produced, well, number one, because I know it's a turbine and I know it's supposed to produce power, but also because that W dot is a positive term. So if you calculate a negative number, that means that you're putting work into it, and you've probably made a mistake somewhere. So, all right, well, I hope that was helpful. Thank you for watching.